Okay, so first of all, I think there's going to be some mistakes in today's lecture, because some explicit computations I just couldn't finish doing some double checking them, and I think there's going to be a couple of formulae that are actually wrong in the lecture. I will try to have them corrected by tomorrow or by Wednesday. But okay, but I will let you know when they come, when they come up. So first, addendum from yesterday. Yesterday there was a gap, right? Yeah, and then this at least I could finish checking. Where did I do it? Okay, now I don't find where I did it, but I feel that somehow I filled in the gap. Did I leave it home? Let's see. No, 1 second. Okay, it seems. Yeah, anyway, so I will try to fill it in live. So let's see. Right, so yesterday we left this as an exercise, yeah, for this function defined on U cross U, yeah, and then taking it for granted, we showed this. Okay, and then I'm not going to repeat exactly how we did it. Yeah, and then we also showed that for every real number greater or equal than 1, we have this is satisfied, and this we did check like kind of in excruciating detail. Okay, and then somehow what I failed to do was to relate this quantity to this invariant quantity. Yeah. Now let's see. Now for all W and Z in U, so let's see. Let's take yeah. Let's take yeah, now I remember where I did it. Sorry. Yes. So I didn't find it because I did it here. Yes. Okay. Okay, so this just saved us from like maybe 5 minutes of boredom, because so can you read it there, or is it too small? So maybe let me zoom in. Yeah. Yeah. So for we want the norm of W minus Z, this square, right? Because somehow that's what we want here. Yeah, and then somehow the idea is to compare the square of this to this quantity. Yeah? So now the square of this is of course this, right? So it's like the number times its complex conjugate, which is fully fully distributed here. Yeah, and then it's also equal to this, but this I don't care. So this was because I was just, it was a failed attempt. So this doesn't matter. Yeah. Right, and then on the other hand, we do have, we have the expression for this is precisely this, again a number times its conjugate, which is fully developed here. Yeah, and then here this also doesn't matter. Yeah. Now the whole point is that I compare this to this, and then somehow I just check what this needs to become this, and then I just add a 0. Yeah, and then what I see is that this is equal to this thing, and then I add a 0. Yeah, and then I recollect this as this thing. Yeah. So what I obtain is that this is just this times 2 times the image of W, 2 times the image of Z, which means that that when I divide by when I take W, when I take W minus Z, let's say square divided by what is it, the square? So it's 4 times the image of W, not the image, the imaginary part of Z. This gives me precisely norm of W minus Z square divided by 4 times the imaginary part of W, imaginary part of Z, and then plus 1, right? Which, by the exercise, is invariant under the action of PSL2R. So in the end, it wasn't really so hard. Yeah, but actually, kind of the time I spent, filling in this gap somehow is the time that I missed, that I needed to double check the other things. So that I'm sure it has a mistake. I mean, I'm like, I don't know, 80% sure. But we will see. Now, let's go. And so we are going to begin moving towards Ptolemy's identity in the hyperbolic plane. Yeah. So first of all, at least in the upper half plane model and in the Poincaré disk, it is clear that there is a boundary at infinity. Right? In the Poincaré disk, it's the unit circle, which doesn't really belong to the model. I mean, it's not really part of the hyperbolic plane, and we think of them as points at infinity. So they are the closure at infinity. And same thing for the upper half plane model, we have R bar as a kind of as obvious boundary at infinity. Yeah. So in either case, like it's a circle that I say it's a circle at infinity. Yeah. And so here when I say H, let's say that I refer to any of these two models, whichever you prefer, and then together with the boundary at infinity is just the corresponding bar, H bar. Okay. So that's this definition. And now, one thing is that I know that two pair of points in the hyperbolic plane determine a shortest curve joining them, but actually the same is true for any 2 points at infinity. And in fact, for any subset of H bar that determines has a convex hull, so hyperbolically convex. Same proof as the usual proof. And what I'm saying is that any subset not only of H but actually of H bar has a convex hull. So here, let me see, upper half plane, basic constructions. Let's say convex hull, and let's say of 2 points is the shortest curve, the so-called the geodesic joining them, and let's say, I mean, if one of the points may be a point at infinity, the other one as well. And of course, I mean, it's sort of obvious if one just thinks about the the fact that that the shortest curves are semicircles or vertical line segments orthogonal to R bar. Or in this is all, it is also obvious if you think about the Poincare disk model that any pair of points in H bar, not only in H, determines a shortest curve joining them. Though of course, if one of the points is a point at infinity, this shortest curve is going to have infinite hyperbolic length. And actually, kind of, if you think about it, it doesn't. It's kind of the shortest curve as a curve contained in H. It doesn't really arrive at the point at infinity in a way. Anyway, yeah. So that would be, yeah, and then of 3 points. So what you are seeing there is a hyperbolic triangle. Let's say, let me zoom in to be able to move this point. Okay, I don't know why I can't move it. Yeah, so a finite hyperbolic triangle, and let's say with one vertex at infinity, with 2 vertices at infinity, yeah, with three vertices at infinity, yeah. But also like quadrilaterals. And then, for instance, here something that I liked about this program is that here you have 4 points, but here you can see this 4th point is actually in the convex hull of the three other points. Yeah, yeah. And then again, you can have some quadrilaterals, all of whose 4 points are points at infinity. Whenever we have a convex, a polygon, all of whose vertices are points at infinity, we just call it ideal polygon. So what you are seeing here is an ideal quadrilateral, and so on, right? So pentagons as well. So ideal pentagon, etc. The angle would be would be 0, right? So yes, and you actually have the beautiful theorem of Gauss-Bonnet that relates the sum of the three angles to the area, right? So I mean, in Euclidean geometry, the sum of the 3 angles of a triangle is always what, pi? It's 360 degrees. In hyperbolic geometry, it's always less or equal than 180 degrees, and it's equal exactly when the 3 points are point at infinity. Did I say something wrong or not? No?
The 3 points are at infinity.
It's sorry. It's not the sum. Yeah, sorry, I mixed concepts. Yeah, you are absolutely right. The sum of them is of course 0, and the area of the triangle is pi minus that. Sorry. Yes, you are completely right. Okay. Now, yeah, thanks for the correction. Yeah. Okay. So that's what I meant here. Okay. Now the kind of the cast of characters for Ptolemy's identity, and it's the main one is the sign distance between horocycles. So I need to tell you what a horocycle is, and I am going to give a non-intrinsic definition, which is not intrinsic, in the sense that it makes reference not to only hyperbolic objects, but to the model itself, to the concrete model we are talking about. So either the upper half plane or the Poincare disk. Now, otherwise, the definition is quite simple. So a horocycle is a circle contained in H bar, so contained in the H union the circle at infinity, which is tangent to the circle at infinity. Yeah. So for instance, so if the model, so let's say if in the Poincaré disk, if this is the Poincaré disk, then a horocycle looks like this. You know, it has to be a circle contained here, where I'm including, of course, this, and then tangent to that, to this outside circle. So, for instance, this would be a horocycle, or this, yeah. And then you know, in H bar, we would have, you know, here is R bar, and then a horocycle. This is a horocycle. Yeah, but then if you consider, you know, tangent to R bar, which is a circle at infinity. At infinity, this would be a horizontal Euclidean line. That's also a horocycle. So this horizontal Euclidean lines are horocycles. And then, of course, you know, since I'm saying subsets of, you know, circle contained in H bar, I would really need, strictly speaking, I have to say horizontal Euclidean line union the point at infinity. Okay, I do that. Okay. There are intrinsic definitions, if I remember correctly, an intrinsic definition would be a curve with a constant positive curvature. And then, I mean, you can have a look at the Wikipedia page about horocycles. Yeah. Because that here, somehow here, you see, I need how to say, let's say in the hyperboloid. In the hyperboloid, what is the circle at infinity? Right? I mean, it's kind of maybe there is a circle. I mean, maybe, but it's not so obvious to see it, right? And then, kind of strictly speaking, the hyperbolic plane would be any Riemannian two manifold, Riemannian isometric to let's say the hyperboloid with Minkowski's form. Okay, in any such two manifold, how do you know that there is a circle at infinity? How do you define it? You see, and the definition I'm giving needs to make reference to that circle. Yeah. Yeah. So an intrinsic definition, if I remember correctly, is a curve of positive curvature in H, and that's the thing is right now I am at least bypassing to I don't have to. I'm bypassing the definition of curvature in H. That's what I'm bypassing with by doing this. Okay, now definition. So now take two horocycles. You know, the tangency points are called the tangency point of a horocycle is called the base point of the horocycle. And so here this would be the base point of this one, base point of this one, etc. Base point of this one, and the base point of this one would be infinity. Okay, now the definition of signed distance between two horocycles. Let me go to the next one, because maybe with a picture it is better. Here I really need to change, instead of BK and VJ, I really need to say like P1 and P2. So maybe here, let me write P1, P2, P1 and P2. Yeah. And then if I have two horocycles based at two different points, I'm going to distinguish two situations. One where the two horocycles don't intersect each other, and the other one where the two horocycles do intersect each other. Okay, when they don't intersect, I define epsilon between the two horocycles to be plus, and if they don't cross each other. If they cross each other, so if the horocycles intersect, or even if they are tangent, yeah, I define epsilon of them to be minus. Okay, so the sign just, when I see epsilon of two horocycles, it's just telling me whether the horocycles cross or not. And that's it, that's all it's telling me. Okay, now, each horocycle is based at a point, which is a point at infinity, in either situation. And as such, these 2 points at infinity determine a unique, let's say, geodesic connecting them, right? So that's the first easy observation I made. In either situation, right? It doesn't matter whether the pair of horocycles, if the two horocycles intersect or not. The two base points determine a geodesic, a shortest curve joining them. Yeah, and this shortest curve crosses each of the horocycles, and the point of crossing happens in finite points. Yeah. So, which I'm going to denote, let's say, Q1 and Q2. Q1 and Q2. Yes, so the first one is correct, the one on the left. On the right, this is Q1 and this is Q2. Okay, and of course the segment cut off has a hyperbolic length, which is precisely the hyperbolic distance between the cutoff points, right? In both cases, right? So this L is the hyperbolic distance, between Q1 and Q2. Yeah, and then the signed distance between the two given horocycles is going to be the exponential of this number, where here there's a typo. Here it's Q1, Q2. Yeah. And then it's the exponential of something to be divided by 2. Okay, what do I divide by 2? The product of the sign, so this plus or this minus, with this length. Yeah. So you see, it's kind of this signed distance. It's pretty much, you take the distance between the crossing points. You just take it with a sign that tells you whether the horocycles crossed or not. Do something quite simple, which is divide by 2, and do another simple operation, which is just take exponential of that. Okay, that's also called, and that's actually usually called, it's more commonly called the lambda length of the geodesic with respect to the two horocycles. So it's somehow. This lambda h1, h2, it's the lambda length of this with respect to these two, to h1 and h2. And also here, it's the lambda length of the same thing with respect to other pair of horocycles. That's the way people usually think about it. Okay, so you see, it's essentially, it's almost just the distance between these two. Okay, one thing, yeah, one exercise that I find nice, because I think it's it somehow shows that some pictures they may be misleading and require some reflection or some thought. So in this case, in the case where I take two horocycles that cross each other, yeah, they cross each other, yeah, and on the one hand. On the other hand, I know that the base points determine a geodesic connecting them. But how do I know that it really that this one really passes through this region, through the region which is the intersection of the two Euclidean circles? How do I know that? I mean, how do I know that it is not the case that maybe my picture is actually deceiving me and something like this happens? You see, and then that I'm taking with minus sign actually the distance of a segment which is not contained at all in the intersection of the two Euclidean disks. So how do I know that happens? That's a good exercise. That if you want, we can discuss. Yeah, because somehow I don't think it's so obvious. And actually, what we have seen about the hyperbolic plane can be used to prove it. If you think about the upper half plane and take one of the two horocycles to be a horocycle based at infinity, so it's a horizontal line. Then any horocycle joining it is crossing it is it's tangent to R bar, and so the shortest curve has to go from a real number to infinity, so it has to be vertical. So you see, it really has to go through the intersection I'm saying, and then you kind of just juggle with Mobius transformations. But otherwise, I don't see it so obvious. I mean,
whereas if you have two horocycles with the base points on the real line, you have two real numbers you have to add, and it has to be an R.
Right. Yes.
So then it geometrically, intuitively does pass.
Right. Yeah. I mean, yeah. So I agree. I agree that somehow if you start drawing things, that this is the things that really comes to your mind first. Yeah, and then so that's why I was saying that it actually required me some thought to realize that somehow it needs proof, because intuitively it's really just clear.
Yeah. Also in H, it could go above them.
Yeah. Right. Yeah. That's somehow the thing. Yeah. That here, you do this. Sorry, no, that's geodesics. Yeah, sorry. You do this. Okay. Assuming this is tangent, how do you know that this is not the case? Yeah, or like this underneath, right? I know that the intuition really that. The intuition really says, no, come on. I mean, that looks more like it. But okay, but how do you prove it?
Is it maybe because the geodesic has to be perpendicular?
Right. Yes, but I agreed. That it has to be, since it's it's perpendicular to both horocycles. So that at the other point of intersection, let's say, since because of this, then here you also have this, and because of this, here you also have this. But to be honest, without moving one of the points to infinity, I couldn't go beyond this, like personally. Yeah, but then when you move one of the points to infinity using a Möbius transformation, then it just kind of becomes practically obvious, no? because you are in this situation. This is one of the horocycles, and then you are saying it crosses this. Yeah, so it's kind of, well, it's obvious that it has to go through the intersecting region. Okay.
In training, that's what we mentioned in the middle point. So the geodesics pass also through the same.
Through the centers of the horocycles? No.
So even though they are.
You mean through the centers of the Euclidean
No.
circles, or through the yeah. Yeah, but the point is that these are not hyperbolic circles because they have one point not in the hyperbolic plane. So these really are not. They don't have a hyperbolic center. They don't have a hyperbolic radius. Yeah. And actually, yeah, some other interesting things happen. Yeah, that I can come back later, later if you want. But yeah, it's okay. Yeah. Now a preparation lemma, which I think is also by Penner. I think this was also proved by Penner in the 80s. I think in the 80s, I think. In 87, I think. If I'm not mistaken. And it says the following. So for the moment, let me not even show the statement, just show the picture. In the picture, it's easier to explain. And of course, in the picture, I'm taking an oversimplified picture in the sense that I'm beginning with 3 horocycles. I'm beginning with 3 horocycles based at 3 different points. Now the oversimplification is that they are drawn without crossings. Yeah. But the definition makes sense also if they cross. Okay. Now the definition is the statement of the lemma, is the following. So for instance, So first of all, each pair of horocycles determines the corresponding lambda length. So the corresponding distance between the horocycles, which in this case, between this and this is it's called the lambda naught, etc. Right? Between this and this, it's this that it's called the lambda 2, and between this and this, it's this which is called the lambda 1, which is not the hyperbolic length of the segment. Is the exponential of something related to that length. Okay, and the statement of the lemma is that if you pick one of the horocycles, anyone, and you look at this segment, the segment of this horocycle determined by the crossing with the 2 geodesics coming out of it. So this segment, in this case, that the hyperbolic length of this segment is precisely this number, which is combinatorially described is just opposite divided by adjacent. Yeah, and the thing is, this is the hyperbolic length, so that is correct. Here one doesn't take hyperbolic length. Yeah, but here one does take hyperbolic length. Yeah, and similarly, the hyperbolic length of this horocyclic segment is this number divided by the 2 adjacent, so which is here, and similarly here for the third one. So this is always, and this is always, even if the horocycles cross each other. Yeah. Now, yeah. So this figure I took from Penner's book, but for the statement of the lemma, I did not follow his convention. So here actually in the statement of the lemma, you see in this figure of Penner, he numbers 0, 1, 2 in the clockwise sense, and what you are going to see in the lemma is that for the statement I numbered things 1, 2, 3 and in the counterclockwise. Yeah? So except for these conventions, that's what the lemma says. Yeah? And it's in the proof that I think there is a mistake. I mean, the lemma is true. The ideas of the lemma are correct. It's just a computation, I think, is incorrect. But so we will see. Okay, so now, I mean, I think it's clear, no, what is being asserted. Now, this of course can be translated to the upper half plane. Yeah? And now the first thing I'm going to say is that working in the upper half plane, we can assume without loss of generality that you know, the first point, the first point, you know, that I pick one of the 3 points, and that this point is the point at infinity. So this I can clearly assume without loss of generality. Do you agree? I mean, because let's say, why? Because if the base point of the horocycle is a real number, well, if it's 0, then I just apply 1 over x, and then it's the image of the whole configuration has that vertex as that point as the point at infinity. Otherwise, it's, let's say, a positive real number. Okay, then first I translate so that it becomes 0, and then I apply 1 over z. Done. You know, and then I can do this also if it's a negative real number. Okay, so it is clear that I can assume that that one of the numbers, that one of the base points of the horocycles is the point at infinity. Now, next, that the one that succeeds this point in the counterclockwise sense is 0. Why? I mean, because I just again to whatever configuration I have of horocycles. Now I already know that I can assume without loss of generality that P1 is infinity. P2 is then some real number. If it's 0, okay, it's already 0. If not, then I apply a horizontal translation to make it 0. Yeah, and then of course I take the original configuration of horocycles and I apply this transformation. Okay, yeah. So good. I can assume this and I can assume this. And now the next thing is that the horocycle based at P1, which then, since P1 is infinity, is a horizontal line, then I claim that I can also assume without loss of generality is that this horizontal line is at height 1. You know? And this is why? This is because when I know it's a horizontal line, I can just multiply by a positive real number to normalize it. Okay, so good. Yes. Okay. Of course, I'm already saying that the signed distance between two horocycles is does not change. Is invariant on their PSL2R, but that's clear, right? That's clear because it's E of whatever. I mean, and then if they cross, their images will cross under whatever transformation, and this distance will be precisely preserved. Right? So it's obvious that lambda lengths are invariant on their isometries of the hyperbolic plane, fact which I am already using for this without loss of generality. Okay, and then since I said that I'm working counterclockwise, and I already have, you know, P1 is infinity, and P2 is 0, and counterclockwise in the upper half plane means that P3 is to the right of 0. So P3 is somewhere here. Okay, and now and then the configuration is that here is H1, which is H1, which is precisely, I mean, it's this on the okay, and then I'm still going to work with kind of with the picture where they don't cross each other, the horocycles, just to have the picture not as complicated, the least complicated possible. Yeah, and let me draw the geodesics. So here you have the vertical one. Here you also have the vertical one, and this, which is you see the third one, the non-vertical one, the non-vertical green one, could cross the horizontal horocycle, no problem. I mean, this one could as well cross this one. I mean, if P3 is very far away. Okay. Now the thing you see is that now this becomes then what is it according to right? So I'm going, yeah. Okay. So now consider this segment. This segment is precisely one of these segments, because it's the segment of the horocycle H1 that goes from that goes from this shortest curve to this shortest curve. This is the point at infinity. So I want to prove that the hyperbolic length of this segment is the product of the lambda length of this segment. Sorry, it's not the product, but it's this lambda length, the lambda length of this segment, divided by the product of the lambda length of this times the lambda length of this. That's what I want. Yeah. So if you want here, I would have the lambda length of H2, H3, which is not the hyperbolic length. Here I would have the lambda length of H1, H2, which again, it is not the hyperbolic length. And here is the lambda length H2, H3. Okay. And this is what I want to compute as a quotient of the of products of the other things. Now it's of course a positive real number, and you see when I graph down the integral that gives me the hyperbolic length of this thing, since I am at everything happened, all the curve is at height 1. The rescaling factor in the dot product that goes in the integral, that it's the integral of a square root of dot product of some tangent vector with itself. The rescaling factor that appears in that dot product is 1, because I'm at height 1. So that's why I did it. You see, because then the hyperbolic length of this just becomes just the usual integral from, let's say, 0 to P3 of square root of just the usual dot product of gamma prime with itself. And actually you can parameterize things just linearly, so square root of 1, if I'm thinking correctly. Yeah. Yes. Which is just P3. So P3 as a positive real number is precisely the hyperbolic length of this horocyclic segment. But I'm going to call it T0 just kind of to distinguish between the point at infinity and thinking about it as a real quantity. So this is T0. This coincides with T0. Okay. Now we abbreviate. We make these abbreviations. So A is lambda between H1 and H2. So this is A. This segment here is A. This one here. This segment is A. But of course, I mean the lambda length. B is from 2 to 3. So this one becomes B. So this is equal to B, and this becomes C. So that's the abbreviations. And what I want to show with these abbreviations is that T0 is equal to B divided by AC. That's what I want to show. Okay. Now the idea is what? The idea is that now, since now I have I have a kind of an Euclidean configuration that is completely tractable, and it may be tedious but tractable. That's the idea. To measure these things. Okay. So for instance, if I want to find this is H2. So let me write that. This is H2. H2. This is H3. Let me copy paste. Yeah. So for example, this circle, this is an Euclidean circle, which is the zero locus of. I mean, it has a circle equation in the Euclidean plane. That one can compute explicitly. No? The point is you see the only point is to find its center and its radius, as we know from many years ago. And now the thing is that of course this is height 1, and then of course the center is related to A, and A is an exponential of something. So how to say? Using that, one just finds the center. That's what I'm trying to say. And then this I really checked in full detail. I have this. I do have the computation that this is correct. Did I do something wrong? Yeah. A is the. It's the exponential, yes. Yeah. No, it's right. It's right. Yes. Yeah. A is the lambda length, not the Euclidean length, not the hyperbolic length. The lambda length, which is exponential of plus minus a hyperbolic length. Yes. Yeah. Yes. And somehow and this is why here it appears in the denominator. Yeah. This I'm sure. This I'm completely sure. Now you made me hesitate.
Just that
yeah, I mean, you have to prove that this one, that the coordinate of this one is 1 over 2a squared. Right? That's it. Yeah. Given that this is the exponential of whatever. Yeah. Yeah. Right. So what you have to show is that this height, this Euclidean height, is this Euclidean height here is 1 over a square. That's what you have to show, right? Yeah. No, it's a yeah. And yeah. And it's I'm not going to say more. That it's not. I mean, it's not 1 over a for instance. Sorry, 1 minus a, for example. No? Okay, and similarly for the center square. Okay. Now this I verified. I mean, okay, Sergio made me hesitate, but this I did check it, and it's fine, you know. And then by the same token, this is correct because it's same situation except that it happens on you know, when real part is t0, is t0, but otherwise it's defined by c. So this one is correct. Yes, and then for this geodesic connecting P2 and P3, you compute. This is really super easy, and you get this. Of course, looking only at y positive. Okay, so this is fine. This is fine. Yeah, and now it's the intersection points, and there are even formulae for the intersection points of two circles in terms of their centers and radii. Yeah? And the idea is to use those formulae, for example, to come to the point that these intersection points. So let's see, this one with H2, which would be the intersection of this one with H2. So this one would be Q2. So maybe let me do it bigger and indicate Q2. So this maybe in magenta in this one here is that one there is Q2, and this one here is Q3. And then one uses that formula, and then one does not arrive at this, because that's where I think the mistake is. I think here it should be a square. I mean, I think here there is a mistake in the denominators, I think. But then, you know, I just didn't have enough time to really check. So here let me put a warning sign. So here, an exclamation mark. Yeah. So the point is the the following, that I'm basing this is based on a paper by Nakanishi, which is included in the references. And then this one, this one I copied from the article, as well as this, for example, as well as this computation. Yeah, and then after copying, then I said like, okay, but let me check if it's true. This one I did check, but this one I didn't have enough time. I ran out of time. I had to come home, so come from home. So let me just double check this. I mean, I think this is square. This is square, but I have to double check. Okay. In any case, after doing this, you see one has the explicit computation of these 2 points, which is in any case doable from this, by like high school math or secondary school math. Yeah. Okay. Now B is this, but the lambda in lambda length. B is this, which is this exponent. This if here I'm saying if the real part of Q3, if the real part of Q3 is greater than the real part of Q2, and here you see I'm already using this fact. Okay, sorry. Let me finish stating this. Or minus this. If in this case you see I'm already using the fact that here here one has to put a plus and here one minus in these situations. I'm already using what I said here, that if they cross, it has to go. The segment has to go here. It has to go there. I mean, it has to be a subset of the intersection of the 2 Euclidean disks. So this exercise I actually already solved. Right? So it's not it's solved. So that's a fact. Yeah, and now using this, now we divide into 2 cases: whether this happens or the case when this happens. So in the first case, we combine. There is this equality, which I think we all know from like our calculus classes, which otherwise, if you just take the definition of hyperbolic cosine or hyperbolic sine in terms of the exponential, this is obvious. Okay, and now B, which is this lambda length, is equal to. Let me think. Right. Yes. So you see, I'm assuming this. So I'm assuming that B is equal to this. So B is the exponential of something to the half, which is a cosine plus a sine. So I just divided cosine plus a sine. Okay, so I used only this identity applied to this. Okay, and now this hyperbolic cosine, by the last formula from yesterday, it's the formula from today is equal to this, whereas the hyperbolic sine, it remained as an exercise to show that is equal to this. Okay, so yes, and then one explicitly computes this. How? Well, knowing an explicit computation of Q2 and Q3. So that's where I need this. Yeah, and then using that, one should arrive at AC T naught. And this is, yeah, this is tedious. Okay, and then of course one has still the other case. Yeah, one arrives at the same. But let's say here, once we are here, that's somehow exactly what we wanted, right? Because we wanted T naught to be B divided by AC. That's what we wanted. Okay, so everything is, everything is, I would say, like super elementary, and even the mistakes are super elementary. Yeah. So let me just double check this, and one has to really check this, which is like super boring. This last equality, but okay. Now, one thing, and I believe so. So as I said, this I just copied from Nakanishi's paper. But the thing is, I think what happened is that he himself copied from Penner's first paper, which then later Penner realized that they had a mistake. So that's I think what happened. Because then later in his book on decorated Teichmüller theory, then Penner says, okay, whatever computation I'm doing now corrects the mistake in the other paper. So I think that's kind of the, yeah. Anyway, yeah. So finally, Ptolemy's identity. Yeah. So now I'm going to start with 4 horocycles based at 4 different points on the circle at infinity. So let's say that these horocycles, yeah. So these horocycles, I'm going to denote them by, I'm just going to be careful to denote them H1, H2, H3, H4. In other words, counterclockwise. Yeah, and then I'm assuming that they are based, let's say, at points P1, P2, P3, P4 as before, and that the corresponding lambda lengths are given, between 1 and 4. The lambda length, well, is lambda 1, 4. So it's the exponential whatever of this hyperbolic segment. Between 1 and 2 is the exponential of plus minus the hyperbolic length, this hyperbolic length divided by 2, etc. So the point is that being 4 horocycles, I have how many geodesics? Well, 4 choose 2, so 6 geodesics, which you are seeing here, right? 1, 2, 3, 4, 5, and 6. And the Penner's theorem, which, by the way, this one is already modern kind of contemporary mathematics. Maybe 2,000 years after Ptolemy, and it's that the lambda length of this segment times the lambda length of this segment, so the lambda lengths of diagonals, is equal to the sum of this times this plus this times this. So they kind of exactly Ptolemy's identity. Yeah, and the proof now using the preparation lemma becomes actually quite simple, because let's say let me call them just A, B, C, D. No, not D. Sorry. Let me do it. Try not to be so silly. How do I want them? Let me call this E and F, and then A, B, C, D. But those are just indices. Yeah? so let's say, so what I want is to prove that I want to prove that lambda E times lambda F is equal to lambda A times lambda C plus lambda B times lambda D. That's what lambda D. That's what I want. Yeah, but what I know is that consider, for instance, this horocyclic segment. I know that it is equal to the sum of this hyperbolic length and this hyperbolic length, because for the horocyclic segments we did take hyperbolic length. So what I know is that lambda F is equal to the sum of two things. Let me see if the sum of two things. Wait. Sorry. I'm doing something silly. That horocyclic segment is this horocyclic segment is this plus this, and then the first horocyclic segment is lambda A divided by lambda F, lambda F, lambda B. So I know that the first segment is lambda A divided by lambda F, lambda B. Okay. Whereas the second horocyclic segment is lambda D divided by lambda F, lambda C. Am I doing something strange? Just 1 second. So this segment is this plus this, yes, and this one is this adjacent, which is F, B and A, yes, okay, and now this one is the same F, and then D and C. Okay, I think it's okay. Lambda D divided by lambda F, lambda C. Okay. Yes, and this is that. Yes, but then if I consider this triangle, the whole thing is equal to the opposite, which is lambda E divided by lambda B, lambda C. So this is equal to lambda E divided by lambda B, lambda C. Right? So for the second one, I'm looking at this triangle, and this horocyclic segment. Yeah. Whereas for the left hand side, I looked at this, which was this one, and at this one, which is this one. Okay. Okay, and now we are done, right? Because now multiply by lambda F, let's say. So you have lambda A, lambda F plus lambda D, lambda F is equal to lambda E, lambda F divided by lambda B. Did I do it wrong correctly? Lambda C, lambda B, lambda C, and then multiply by lambda B, lambda C. So you have lambda. What did I do wrong? Sorry?
You have multiplied by lambda F. It's not on the left side. There is no lambda.
Yes, thank you. Oh, yeah, okay. This I really have to edit in the video. Yeah. So yeah, okay. And now multiply by lambda b lambda c. So it's lambda a lambda c plus lambda d lambda b equal to lambda e lambda f, which is what we wanted. Okay. So really, the kind of the hard part is the preparation lemma. Okay. Yeah. So there it is. Now it is important to say, I mean, to notice, it's for every 4 tuple of horocycles ordered this way, right? Ordered counterclockwise. But it is always true. I mean, it doesn't matter what horocycles you pick at the point, as long as the 4 points are different. And we will see this is what makes it, what gives it a significance when one passes through some certain moduli spaces.
So is this in any way related to Plucker relations? Like this looks like a Plucker relation.
It is a Plucker relation, yeah. Yes and no. I mean, what will happen is that what happens is that lambda lengths, which are really which are going to be each lambda length is going to be a function from certain Teichmüller space to the real numbers, and these functions satisfy the same identities as the Plucker relations, but the Plucker relations they really are functions from the Grassmannian to the complex numbers, right? So at that level, it's only an analogous behavior, yeah. But then you can force the machinery a little bit in order to show that somehow the decorated Teichmüller space is the totally positive part of the Grassmannian, if I'm not mistaken. So it's kind of, you can force it in order to see that that it's not only an analogy, it's really because it's an inequality, it's an equality happening on a subset of a bigger space. And this Fomin and Thurston do talk about this in their paper. So maybe let me, yeah. So there's this paper by Fomin and Thurston, and they do say some words about that. Yeah, but at the moment I cannot tell you more than that. Yeah. But it is true. I mean, yeah. I mean, yeah. Okay. I don't want to disorganize my head too much, but yeah. But this is in the let's say in the Grassmannian in this Grassmannian. Right. Yeah. I mean, this is because, yeah, these are Plucker coordinates, and then if you think about it, it's in this for this quiver, not this quiver Grassmannian, for this Grassmannian. I can try to maybe I can try to prepare something about that, but at the moment, the thing is, at the moment I don't want to say too much because it's going to be, like just disorganized thoughts. Yeah. Okay. Yeah, but it's really nice that you observed that. Yeah. Now the decorate. This is not decorated. This is just the Teichmüller space of triangles. This is very boring, and it's just kind of to make a point. So somehow the problem is the following. You know, it's how many hyperbolic ideal triangles are there up to isometries of the hyperbolic of two isometries that preserve the hyperbolic metric. Ideal triangles, right? So triangles, all of whose three vertices are points at infinity. And as Professor Tomasi did, I'm going to take, I'm going to order the vertices, just kind of to make my life easier, because, yeah, I mean, you have seen, right, that when one thinks, like when she spoke about like moduli spaces of triangles or of Riemann surfaces, when the marked points were ordered, things became easier. So same exactly because of the same reason. So for the same reason, I ask about hyperbolic to try to classify all hyperbolic triangles up to isometry. But of course, where I think, okay, ordered, or with ordered vertices, and also oriented counterclockwise. Yeah? So I want somehow to classify all such things where I'm thinking that there's a first vertex and the triangle is oriented counterclockwise, which means when I say, okay, P1, P2, P3, is really I'm considering it a different object as P1, P2, P3, for example, and P1, P2, P3. Yeah, and then formally, how do I do it? By just speaking about ordered triples of points lying on the circle at infinity and oriented counterclockwise. That's it. Okay, and then up to hyperbolic isometries. Well, we have the simple transitivity on triples of distinct points. Yeah, and then you see, there's only all of the any two such triples are equivalent under a unique isometry of the hyperbolic plane. So in other words, when you consider, T of the triangle, T of the triangle, and T, what I mean is a Teichmüller space, which, let's say, define to be, set of P1, P2, P3 in the circle at infinity with, excuse me, they all different. So P1, P2, P3, they all different, right? So the cardinality of this equal to 3, and moreover, oriented counterclockwise. See, counterclockwise. This modulo, what would be in this case, since I'm drawing the Poincaré disk, it would be PSU11, right? And the thing is, and this is this is why I said it's boring. It's just one point, because of simple transitivity. yeah, on triples of distinct points. I mean, here, if you give me two such triples, I would take the unique Möbius transformation, taking one order triple to the other, and well, it preserves the disks because all of what we have been saying, right? I mean, it sends it has to send it sends circles to circles. Both of the circles have to be the circle at infinity, because both order triples lie on the circle at infinity, and since both triples are oriented counterclockwise, the image of the disk cannot be the outside; it has to be the disk itself. Yeah, and then once you have that, you have established that any two such triples are equivalent under PSU11. Okay, so that was boring, and now of hyperbolic quadrilaterals. Again, okay. First the undecorated version, and then the decorated version. So first just the usual Teichmüller space without decoration. So now the problem would be, again, kind of the moduli problem is when first presented, someone says, okay, classify all possible. Actually, someone would actually say, classify all possible ways of putting a hyperbolic metric on this Euclidean quadrilateral, yeah, in such a way that it's hyperbolic on all of this, and this becomes point at infinity, and the four sides become geodesics. So that's actually how some people would say. And then one would need to say, okay, so let's translate it to something more tractable, right? Because you are telling me in how many different ways I can put a metric, a certain type of Riemannian metric here. Okay, no, it's better if I just go to the hyperbolic plane, and then in the hyperbolic plane, I ask myself about ideal quadrilaterals in the hyperbolic plane, and to make my life easier, at least as a first step, I take ordered ideal quadrilaterals, by which I mean ideal quadrilaterals in which I have a first vertex, and then the rest of them I think of them as ordered in the counterclockwise sense. So in the end, one kind of cooks up the definition of the Teichmüller space of a square, which would be is like pretty much the same definition here, but with 4. And here, of course, it's not S1. It is S1 to the third. Yeah. And here now it's going to be S1 to the fourth. And then, of course, I'm kind of behind the curtains. I'm actually telling you that this definition, that this space that we are defining, solves a moduli problem. But somehow, if you notice, I mean, I'm just defining it as a certain quotient, but somehow the complementing with Professor Tomasi's course, somehow the idea is that this space solves a moduli problem.
The space solves a moduli problem, or the space quotients another group like them?
No, it solves a moduli problem, but where you where in your where the class of objects you want to classify, you have added more information to each object in that class, so that with more information you kill the automorphisms. So, and this extra information is that I'm telling you that there's a first vertex.
Yeah, so the orientation kills all the rotations, which would be automorphisms.
Yeah. So the thing is, if you want, the Riemann moduli problem would be the space of quadrilaterals in which I have not singled out a vertex as important, and the Teichmüller version is the space of quadrilaterals in which each object to be classified is a quadrilateral with a distinguished point. So it's not the same as the other moduli problem. And then what I'm saying is that for this other moduli problem, this would provide a moduli space. But it's somehow, you see, it's kind of easier to solve, but in a way, in certain way, less interesting than the Riemann moduli problem. Yeah, and then what I just said, the corresponding version also for Riemann surfaces exists. Like the complete analog thing happens. Yeah. So it's kind of it's kind of the Riemann objects together with some extra marking in such a way that you kill the automorphisms. Here, for example, this ideal quadrilateral. If you think about it only as a subset of the hyperbolic plane, without singling out any vertex, this one has a rotation by 90 degrees as an automorphism. Okay, but if you consider this other, let's say, moduli problem, saying this, giving this object, is different as giving this object. For example. Okay, now 26 seconds. So now you see, again, the thing is, using the simple transitivity on distincts of triples of distinct points, I can say, any such thing has a representative where P1 is I, P2 is -1, and P3 is -I. Okay, and then you have 1 degree of freedom, which is all the open interval between P1 and P3. So T of the square is going to be one-dimensional because you have 1 degree. At least intuitively, it's clear that you have 1 real degree of freedom. Okay. So see you tomorrow.